This video will show a practical example of the Knoevenagel condensation and then discuss the theory. First you'll see me getting dry THF and then weighing out first 1 gram of aldehyde and then 3.93 grams of malonitrile. The compounds are then poured into a round bottom flask and 30 ml of THF added. Subsequently 30 microliters of piperidine to catalyse the reaction is added and the solution is heated to 55 degrees Celsius overnight. The reaction is now allowed to cool before filtering off the product as a precipitate. The precipitate was then washed with 3 times 1 ml of 0 degrees THF, and then the solids collected and an NMR ran to determine the purity of the product that was formed. Subsequently, the compound was dried under high vacuum and another NMR ran to determine the purity, which was high. Finally, the product was weighed to determine a yield of 64%. It is likely that some of the product is also in the solution, although this may have overreacted. The Knoevenagel condensation reaction occurs by the deprotonation of acidic CH2 protons. In order to be acidic, they must be close to a highly electron withdrawing group, or extensive conjugation. Here the cyano groups are electron withdrawing. This deprotonated intermediate then reacts with the aldehyde to break the carbonyl. Proton transfer then occurs, allowing the OH to act as a leaving group on subsequent deprotonation. The product often can react further at this point via Michael addition. However, in the shown reaction, the product precipitates out of solution, preventing further reaction. Note, an alternative explanation is that the Michael addition product stays in solution, leading to no required purification. When this reaction is carried out, it is recommended to carry out the reaction in dry conditions by some works, with some even suggesting adding drying agents to push the equilibrium to completion. Interestingly, there have been some reports of carrying out this reaction in water, so it is unclear how much the reaction occurs in a equilibrium. It is likely dependent on the precise reaction that is studied. Whether the reaction is in equilibrium or not does seem to depend on the system. A crude calculation of the enthalpy of reaction from the breaking of a carbonyl and 2 CHs and the forming of 2 OHs and 1 C does suggest the reaction should not occur on enthalpic terms. However, such an analysis discounts the effect of extending conjugation, which is inevitable due to the aforementioned necessity of acidic CH2 protons. It is the extent of stabilization of the conjugation which will likely determine the reversibility of this reaction.